here I would like to mention something about the PCI injection rate. So, nowadays in fact in some of the furnace PCI injection has gone up to 250 kg per ton of hot metal. And so, nowadays the blast furnace they operate at a very low coke rate, which is around 300 kg per ton of hot metal. So, that is a significant improvement with the PCI. So, but beside PCI we can have this liquid and gaseous fuel, and previously liquid fuel was quite common because due to the availability and economic of it, they were quite cheap actually in comparison to coke and other. So, due to save, so economically they were more viable. So, all liquid fuel light and heavy are hydrogen bearer and carbonaceous, and have carbon and hydrogen bonds. So, for which to break it you need the heat, and due to that they are not completely one in front of the TUA, the time which they have actually. So, the flame temperature always is lower when we use the liquid fuel. So, if one consider general formula like CH2 of this type for fuel and 100% methane for natural gas, the reaction would be something like that, where this is the oxygen and remaining, because we are doing this in terms of presence of air, where quite a lot 80% nitrogen is there, depending if it is a enriched oxygen blast or what. So, you can write the balance equation and enthalpy for the reaction for natural gas, which is mostly comprising with methane. Similarly, you can write this equation where hydrogen and CO is forming. Look at this product. The product actually is CO and hydrogen. So, this is highly reducible. So, reducing power of this is increasing due to the hydrogen, and hydrogen is much more stronger reducing agent than carbon monoxide. So, the flame temperature of some of the fuels is given here. So, flame temperature is very important. Usually it is around between 2000 to 2200, that is the aim to keep it. So, but depending on the other condition. So, if the blast gas temperature is about 900 and oxygen, so which is just a normal air, and carbon is the fuel. So, let us say just only PCI injection is there, then your flame temperature would be around 295. Now, instead of carbon, if you are using fuel oil, see how much decrease in the flame temperature, very low. And natural gas, it is even lower, carbon gas is even lower. So, probably these are not even correct to use it, that may probably create more problem, more volume and things in the blast furnace. So, one has to look at the whole chemistry and the volume of it, and then must use the right combination or right fuel. And when you increase the this blast temperature, you can see the flame temperature of all of those increases, but again the flame temperature of natural gas when using natural gas as a fuel or carbon gas is hardly reaches more than 800 or like that. So, these are really not a very good choice for the fuel. They can be combined with some other. So, many times you use the oxygen rich blast, which usually increase the flame temperature. Fuel oil is okay. So, this gives an idea about the flame temperature. So, flame temperature, that is the highest sort of temperature which is prevailing in the raceway region or in the cavity region, and that is where the flame temperature comes into picture. Now, we talked about the preheating blast temperature, blast air. So, this is about the, if you do not preheat, then to combust 1 kg coke, you need actually 5 kg of air. That is a huge volume. And remember, in this 5 kg of air, 80% is your nitrogen, which takes away your sensible heat and other thing, and it increases the fuel rate, the coke rate, and which really you do not want. So, it is always good to heat it, heat the blast air for reducing the coke rate and efficient burning of the coke. So, air is preheated, and considering the complete combustion of coke at 1400 degrees Celsius, one can again write the chemical equation for that. And if normal air blast, because it had 21% oxygen, so that then one can get the moles of nitrogen. This gives the volume about 4.44 normal meter cube per kg of carbon, and a tear gas volume comes to this. So, volume also reduces in that way, and this tells you how you can get the flame temperature and so the tear gas temperature. So, this is the blast temperature, which like preheating the blast. So, Tv is the blast temperature and Tf is the flame temperature. So, for this case about the blast air, when we are doing at 1400 or complete combustion of it, it is preheated, there is a sort of a correlation by which you can calculate the flame temperature. So, 2300 here it is showing the heat of combustion of carbon, 540 is showing the heat content of the carbon at 1400 degree this. Okay, so here we can have a sort of a correlation between the blast temperature and the flame temperature, which is given below. So, Tv is the blast temperature and Tf is the flame temperature. So, 2300 is the heat of combustion of carbon to CO in kilocalories, and 540 heat content of carbon at 1400 degrees Celsius in kilocalories, and 0.33 is the heat capacity of air in kilocalories per normal meter cube, and 0.33 hat is the heat capacity of the tear gas. And this adjoining figures shows that how so if you know the blast temperature, from this you can calculate the flame temperature, so or vice versa you can have it if you need a particular flame temperature. So, what sort of preheating of the blast needed, you can do that. And this adjoining figure is showing about the tear gas temperature, is nothing, it is a flame temperature, and the blast temperature. So, these are the blast temperature curve, and this is actually the percentage of oxygen. So, oxygen enrichment if you put it. So, 21% is representing the normal air, and this is the enrichment with the of the air with oxygen, and from that one can easily calculate whatever the heat content of the two air gases are, the flame temperature or gas temperature, or the heat content of the gas, or the blast temperature, that gives an idea how to control the flame temperature by changing these variables. And because this is very important, the flame temperature for burning of the coal and producing the reducing gases at the right temperature, which has to go up to the top. So, this is an important parameter. Similarly, many times to increase the reducing capability of the gases or even reduce the sometime temperature, you humidify the air. Humidification means you somehow add some water into it in the air. So, many times blast temperature is required to increase without increasing the flame temperature. So, this is done by adding some coolant in the blast, which is mostly water due to its endothermic reaction. But here one thing must be remember, you do not add water directly in the preheated air, because that water has to evaporate and will consume the heat, and it will reduce the blast temperature, and other problem also comes. So, usually what you do, you put this water in the stove when you are sending the cold air. During that time you do it, and with that you humidified it and it comes, and from this you can see you are really getting a double volume of the reducing gases, CO and hydrogen, when you put the water from the one. So, your reducing power increases, and because it takes the heat and thermic reaction, this also reaction called the water shift reaction. And as you can see, as you increase the water content, your flame temperature decreases, or you can have a blast temperature decrease to maintain the same flame temperature. If you want to maintain a 2000 degree flame temperature, so either you can put 20% water at this preheating, or you can preheat the blast temperature can be up to 800 and 30%. So, like this you can know how to control your blast temperature, keeping the flame temperature constant, because that is more important than this. But this is also important, sometimes you do not want to go really up to 700, you want to go probably a 1000, then you should know how much moisture or humidified you have to make this blast or put the water. So, these things has been done with many experiments and have been put forward that figure. Similarly, as we said, when we say about the flame temperature, many times this is known as the raceway adiabatic flame temperature. So, as pulverized coal injection reduces raceway adiabatic flame temperature or flame temperature, as we were referring before. So, usually oxygen enriched blast is used. To calculate the RAFT, which is nothing the short form of raceway adiabatic flame temperature, following formula empirical correlation has been proposed, and all the units actually are in SI. So, because this is an empirical correlation, so there is no theory behind it. With the many experiments, people have proposed this relation. So, BT is blast temperature, BM is the blast moisture content in gram per meter cube, O is oxygen enrichment. So, whatever like 25% when we said, essentially you are putting a 4% oxygen enrichment, because 21 is already present in the air. Similarly, this is WC is the wind consumption. So, coal per wind consumption in meter cube per ton hot metal. Similarly, the oil, dry oil injection rate divided with the wind consumption. Similarly, the tar, dry tar injection rate, natural gas injection rate in kg per ton of hot metal. So, based on this, one can roughly calculate what would be the flame temperature. If one is not using natural oil or something, then certainly this term will become 0. So, one should not consider this one. Now, how to use this one? One example is given here. So, suppose the blast temperature in a blast furnace is 1000 degrees Celsius and its moisture content is 10 gram per meter cube. The blast volume of 7000 meter cube Tp per minute is entering through the TUR. The oxygen content in the blast is 25.6%, which means it is a enriched oxygen blast, which has about 4.6% enrichment. And the only auxiliary fuel injected in the blast is pulverized coal with injection rate of 200 kg per ton of hot metal. So, one has to find the flame temperature in the above condition. The production rate of the blast furnace is 10,000 ton hot metal per day. So, really we need wind. So, if you look at the formula this, so we have to use this one because we are using pulverized coal, blast moisture, blast temperature, oxygen enrichment, but other things are not coming into the picture, but we need also the wind consumption. So, in meter cube per ton of hot metal, and directly it is not given as such, blast volume is given. So, we have to calculate that one from the production rate and combining blast volume. So, production rate is 10,000 ton hot metal per day, which will give you 6.94 ton hot metal per minute. So, 24 into 60 is going to convert your day into minutes. So, wind consumption would be, when you divide this ton hot metal per minute, will give you the in the meter cube per ton of hot metal. So, 7000 meters cube per minute you are having. So, that is a meter cube per minute actually, that is going to give you the ton of hot metal. So, once you got WC, other values are given: the blast temperature, blast moisture, oxygen enrichment 4.6, and the coal rate is also given. You can directly put into the formula, and in this formula, so 0.82 into PT is 1000, your BM is 10, O is 4.6, and then your coke rate divided by wind consumption. This, so flame temperature comes 2135, and that seems quite reasonable, as we have seen in the previous table of this one. So, that seems very reasonable flame temperature in that condition.